Hello all, welcome to this video on Operating Systems Lab. Today I'll be talking about familiarization with basic Linux programming commands. Operating system programming involves direct interaction with system resources, processes, and executable binaries. Proficiency in system level command line utilities is essential for analyzing program behavior, monitoring system performance, and debugging applications in a Linux environment. Process management tools such as PS and TOP provide information about active processes and resource utilization. Commands like strace, time, and GDB support system call tracing, performance measurement, and program debugging. The fuser utility assists in identifying processes accessing specific files or system resources. In addition, binary analysis tools, including strings, objdump, NM, and file enable inspection of executable and object file structures. Low-level data examination commands such as OD and XXD allow analysis of file contents at the byte level. Collectively, these utilities provide essential capabilities for understanding program execution, system interaction, and binary composition, thereby forming a foundational skill set for effective operating system programming. We'll begin by looking into the command ps. PS command in Linux is the abbreviation for process status. It reports a snapshot of the current process. By default, it will select all processes with the same effective user ID as the current user and associated with the same terminal as the invoker. It displays the process ID, the terminal associated with the process, the accumulated CPU time, and the executable name. Output is unsorted by default. Some of the key practical uses of PS include monitoring system performance, identifying and terminating unresponsive processes, filtering processes by user or name, and checking process uptime. The command run is PS. Its fields include the process ID, TTY, which is the controlling terminal. Now PTS /0. This is referring to a pseudo terminal sleeve, which is a terminal emulator used in graphical sessions. It indicates that the process is running in a terminal that is not directly connected to a physical device, typically used for remote sessions or terminal emulators. Then we have the cumulative CPU time, followed by the command that started the process. We have different options in PS. -A or -E will select all the processes. The command is ps-a. The fields are the same. So here for the controlling terminal, there is a question mark. This means that the process is not associated with any terminal, which is common for background or detached processes like daemons. Followed by the CPU time, which is the cumulative CPU time, and the command used that started the process. Next option is hyphen lowercase a. This will select all the processes except both the session leaders and processes not associated with a terminal. The command is ps-a. The fields are the same. PID, controlling terminal, time, and the command. Next option is T, which will select all processes associated with this terminal, which is identical to the lowercase t option without any argument. The command is ps uppercase T. Here the fields in the output are process ID, the controlling terminal. We have an extra field called the process state. So here SS means that the process is in an interruptible sleep state and it is a session leader, but it is not in the foreground. R plus meaning it's a foreground process that is actively running or ready to run on the system, followed by the time and the command that started the process. Now option R will restrict the selection to only the running processes. So the command is ps followed by R. Here also we have the fields named as PID, the controlling terminal, the process state, time and the command. We can also do process selection by a list. So this option will accept a single argument in the form of a blank separated or comma separated list. This can be used multiple times. So the option will be P followed by the PID list. So the command will be ps space P space the IDs of the process. Here it's 1 and 2. So we have the process IDs in the output, the terminal, the question mark again, showing that these processes are not associated with any terminal. They are usually a background or detached process like a daemon. Then the process state followed by the time and the command. -C is used to show the different scheduler information for the -L option. So the command will be ps-c. So we have the process ID followed by the scheduling class of the process. TS stands for time sharing. Then we have the priority of the process followed by the controlling terminal, the time, that is the cumulative CPU time, and finally the command that started the process along with its arguments if any. Next option is U, which will display the user-oriented format. So the command is ps space U. The fields here are the user, which is the effective username, which is usually the user ID, followed by the process ID, then the CPU utilization of the process. So that is the CPU time used divided by the time the process has been running, which is expressed as a percentage. Then the percentage of physical memory a process is using, that is calculated from its resident set size, that is relative to the total system memory. Now a resident set size refers to the amount of physical memory that a process is currently using in RAM. Then we have the virtual memory size of the process followed by the resident set size, which is the non-swapped physical memory that a task has used. Then the controlling terminal, then the process state. Here SSL plus stands for the case when the process is in interruptible sleep state, is a session leader and is in the foreground process group. SL plus, which states that the process is in interruptible sleep state, is a session leader and is in foreground process group but not currently running. SS for a process in interruptible sleep state and is a session leader but not in the foreground. R plus for a process that is running and is in the foreground process group. Then the starting time or date of the process. If the process started within the last 24 hours, it will show the specific time. If the process started more than 24 hours ago, it shows the date. Then we have the time, which is the accumulated CPU time, which will include both that of the system and user, which will include the minute second format. And finally, the command that will display the command that initiated the process. Next option is V. So that stands to display the virtual memory format. So the format is ps space V. So the fields here are the process ID, the controlling terminal, then the process state, followed by the total accumulated CPU time that the process has used since it started, which will include the minute second format. Then we have the number of major page faults that have occurred with this process. Then the text resident set size, the amount of physical memory devoted to executable code. Then the data resident set size, the amount of private memory reserved by a process. the resident set size, that is the non-swapped physical memory that a task has used, then the ratio of processes resident set size to the physical memory on the machine expressed as a percentage, finally the command that initiated the process. Next is option E, which shows the environment after the command. So the command is ps space E, that will include the process ID, the controlling terminal, the current state of the process, the total CPU time used by the process since its inception, and the command that initiated the process along with its arguments. The uppercase S option will sum up some information such as the CPU usage from dead child processes into their parent. This is useful for examining a system where a parent process repeatedly forks off short-lived children to do the work. So the command is ps space uppercase S. The fields here are the process ID, the controlling terminal, the process state, the total CPU time used by the process since its inception, and the command that initiated the process along with its arguments. Next command is strace. This is a useful diagnostic, instructional, and debugging tool. It runs the specified command until it exits. It intercepts and records the system calls made by a process and the signals a process receives. Each line in the trace contains the system call name followed by its arguments and parentheses and its return value. So the option will go like -e followed by the expression. The format of the expression will be the qualifier followed by the value. In order to trace a particular or specific system calls, the command is strace -e trace equal to write ls. So this command will execute ls and use the strace to intercept and display only the system calls related to writing data. This is the sample output. Here we see each line represents a write system call. So this 1 is the file descriptor for the standard output, where the output of ls is being written, followed by the string buffer containing the data that is being written to there, followed by the number of bytes requested to be written, followed by a return value, indicating the actual number of bytes successfully written to the standard output. The final line exited with 0, which means that the command finished successfully without any errors. 0 means that is the exit status, which shows it was successful. Now the command as trace -e trace equal to network nc -v-n 127.0.0.1 followed by 53. Now this will run strace that will attempt to connect to the IP address 127.0.0.1, which is the local host on port number 53 using the netcat, that is nc utility, and trace only the network related system calls. This being the sample output, can see there is socket functions which is creating and connecting using the AF Unix, that is the Unix domain sockets. We have the connect function. Now these calls are failing, as you can see here, because the specified socket file does not exist, resulting in the no such file error code. Then we attempt the AF inet TCP connection. So after the AF Unix fails, the process falls back into a standard IP version 4 AF inet TCP socket connection. It will also initiate a connect function. So that also starts attempting for a connection. Then there is a get socket option function also. This will check the status of the asynchronous connection attempt. So it returns with an error code showing there is no service listening on port number 53 on the local machine. So the utility prints out with the exit status of 1 showing it was a failure because it couldn't make a successful connection. Now, in order to count the number of system calls, the command is strace -c ls. So the fields here are the mode time, which contains the percentage of total time spent executing that specific system call. Seconds, which is the total time in seconds spent within that system call. Then this field is the average time spent per invocation of that system call in microseconds. This is the total number of times the system call was made. Then we have the errors, that is the number of times the system call returned an error. Then this is the name of the system call. And this is the result of the ls command, which will display all the files and directories there. Now the final line will indicate that a total of 103 system calls were made during the execution of this command, which resulted in 5 errors. Next option is to print the timestamp of each system call made. So the command is strace -r pwd. So it will list the sequence of system calls made by the pwd command and prefix each call with the time difference since the start of the previous system call, whose sample output is given here. So here we can see the time and the calls made related to it. Since this listing was a success, it returned with a exit status of 0. Next, we'll try to print the output of this command to a file. So that is done using strace -o. The name of the output file can be something like output.txt followed by the command. Here we choose pwd. So this is the result of this command, where the output of this command is written to this file output.txt. Next, we'll move on to the gdb command, which is the GNU debugger. The purpose of a debugger such as gdb is to allow you to see what is going on inside another program while it executes, or what another program was doing at the moment it crashed. You can use gdb to debug programs written in C, C++, Fortran and Modula 2. gdb is invoked with the shell command gdb. Once started, it reads commands from the terminal until you tell it to exit with the gdb command quit or exit. Now this is the sample program we'll be using to run this particular command. This program is for adding 2 numbers and the name is program.c. Now we'll start by compiling the program with the debugging symbol, which is -g, and then loading it to the GDB. So the command will be gcc -g, the program.c, that is the program name, followed by -o program. So this will be the name that is given to the object file, which is program.c's compiled output object file. So that name is program. So that is given as program. Then we give the command gdb space the name of the object file, which is program. So to begin, we need to give the run command or R command that will start or restart the program. So whose output is shown in the screenshot. So there, after running it, you can see they have started to read the symbols from the program. So after that, after the compilation and running of GDB program, we give the run command. There they are starting the program and they are asking for entering the two integers. I gave the values 1 and 2 and the sum is printed as 3. Now the execution is done and it exited normally. Now it is waiting for the next command. The option break or B will set the breakpoint at the start of the main function. So which is shown here as B and the function name main. So the value we'll get as output is the breakpoint followed by the breakpoint ID number, which is here 1, and it is given at a particular address. So that is a memory address where the GDB actually placed the breakpoint instruction in the program's compiled machine code, followed by the statement file program.c line 5. There the GDB links the machine address back to the source code file and the line number 5 will correspond to the start of the main function. Then we have another option for break, which will set the breakpoint to pause execution at the specific line number. For example, we give the command B14, then it pauses at line 14, which is shown here. We'll get a similar output with the GDB assigning an identifier 2 for the second breakpoint. This being the internal address in the executable where GDB has placed the halt instruction. This being the information where the breakpoint was actually set in the source code. You can see that the request for breakpoint was made at 14, but the line number is 15. Now what GDB does is it places the breakpoint on the first executable line of code at or after the requested line number. The line number 14 might have been a comment, a blank line, or a declaration, or a brace, none of which are executable. So that was placed in line number 15. Next option is list or L, which will display the source code around the current execution point. So option L will give the output, which is in the screenshot given here. Next, we'll list the lines specified in the command. For example, lines 1 to 4 needs to be displayed. We give the command L1, 4, listing lines 1 to 4. Then we have the command next or n, which will execute the next line of code, stepping over any function calls. So the option n. So we saw that the program wasn't running. So the program was run. Then it faced a breakpoint 1 where I gave the command n. And this was the next line which was executed. So in the sample program considered here, there is no function calls in the code. So the next option, step or S, will also give somewhat a similar output as next. So step or S is used to execute the next line of code stepping into any function calls. So giving the option S, it will give the next line of code which is executed. Then there is the option print or P, which will print the current value of a variable or expression. For example, we give P space num1. So num1 is the name of the variable into which the numbers to be added, one of it is stored. So its result is $1 followed by a value. So this $1 is a GDB internal variable reference. GDB stores the result of every print command in a history variable. So you can reuse the value in subsequent commands. Followed by this value, which is the current value of the variable at that specific point in the program's execution. Similarly, we can also print the value of sum minus num2. Num2 is the other integer which will be used for addition in the program. And sum being the variable to which the numbers are added and stored. So sum is stored there. So there also we have a GDB internal history variable $2 followed by a value at that particular moment in the program's execution. Next option is continue or C, which will continue the execution until the next breakpoint is hit or the program finishes. So C, after that it's showing continuing and it's executed. Then there is the backtrace or BT command, which will display the call stack or stack trace to see which function called which. So this is the output for that command. Here #0 meaning it's the current stack frame. The higher numbers would indicate that the functions called the current one. That is, the higher numbers 1, 2, if they are stated, it means 1 and 2 were calling the stack frame 0. Then the main function where the program is paused, and this is the exact location in the source code file where execution is currently halted. And finally, we have the quit or Q command, which exits the GDB debugger session. Next command is strings. Now this prints the sequence of printable characters and files. For each file given, GNU prints the printable character sequence that is at least 4 characters long and are followed by an unprintable character. Depending upon how the strings program was configured, it will default to either displaying all the printable sequences that it can find in each file or those sequences that are in loadable initialized data sections. If the file type is unrecognizable or if strings is reading from standard input, then it will always display all of the printable sequences that it can find. It is mainly useful for determining the contents of non-text files, the basic syntax being strings followed by the options and the file names. In order to display the printable strings within /bin/ls executable file, we give the command strings /bin/ls. So this is the sample output. So there we will see that the first line is the dynamic linking line that indicates that the dynamic linker or loader that started the program. Then we have the libraries listed here. Then we have the function names, some of the error messages that occurred, also some system interaction that happened. Next option is -a -all, which will scan the entire field instead of just the default sections. So the command is strings -a/bin/ls. Now this also contains libraries and linkers specified, the function calls and embedding strings in it. Next option -n min length --bytes is equal to the min length. Now this will set the minimum string length, which was default as 4. For example, if we need at least 70 characters long strings, we give strings -n 70/bin/ls, which is given here. Now this output is ls colors configuration with some of the color codes, the file type mappings, some of the ls command options which are specified in it. Then we have the -f or --print file name option, which will print the name of the file before each string. This is useful when processing multiple files. So the command is strings -f/bin/ls and /bin/whoiam. So in the output, you will see that those belonging to ls is preceded by that file path and those of who am I is preceded with that file path. Next is -t radix or --radix equal to radix. So this will print the offset within the file before each string. The radix can be a decimal D, octal O or hexadecimal, which is X. Now to print strings from ls with their decimal offset, we give the command strings -t d /min/ls. Just this. Here we have some of the shared libraries, function names and internal data. Now this offset will refer to the specific memory location or position within the binary file where a particular string or text will begin. For example, you take line number 4497, which means the string, which is this, starts exactly 4497 bytes into the /min/ls file. Next option is -e encoding or -- encoding equal to encoding, which will specify the character encoding to search for. Common values include lowercase s for 7-bit ASCII, capital S for 8-bit, B for 16-bit big endian, and L for 16-bit little endian. So the command is strings -e lowercase s /min/ls. So this is displaying the 7-bit ASCII, which is the default. Here also we have some of the shared libraries, function names, error messages and internal data that is displayed. Next we have objdump. So objdump displays the information about one or more object files. The options control what particular information to display. This information is mostly useful to programmers who are working on the compilation tools as opposed to programmers who just want their program to compile and work. So the object file list are object files to be examined. When you specify the archives, objdump shows information on each of the member object file. We'll begin with the option -d, which will disassemble the executable sections of the object file. So first of all, we'll compile it, gcc-o program.c. Then we give the command objdump -d program. So this is the sample output. So this line here will be specifying the file format, which is the standard executable and linkable format for a 64-bit system running on an x86 architecture. Then we have different sections including .init, .plt, which is the procedure linkage table. Then we have the assembly code with the memory address, the row hexadecimal machine code, and the human readable assembly language code and the operands. Now this is used by programmers for debugging, reverse engineering, or to understand how the compiler translates C source code into machine level instructions. Next option is -s. Now this requires the program to be compiled with debugging symbol -g. It is useful for reverse engineering or debugging at the assembly level. Now what this does is it will interleave source code with this assembly. Similarly, as in the previous command, we'll compile the program and we'll run the command objdump -s program. So here we have the same lines of code here in the beginning. So after that, we have this section here where we'll have the memory address of that's the virtual memory address, the machine code, which is the hex bytes, the assembly instructions, and also you can see the C program code in between, which is interleaved with the disassembled code. Next option is -t, which is to view the symbol table. This will display a list of all symbols, which is functions, global variables, static variables, that is defined or used within the file along with their addresses, types and sections. The command is objdump -t program. So the fields here are the address or value, the virtual address where the symbol is located. Then we have the flags or the binding here. Here L stands for local, meaning the symbol is only visible within the specific object file. Then there is the section type. D will refer to a debugging or a dynamic symbol. Then there is this section where the symbols are defined like .text, .data, etc. Then there is the size or the alignment, that is the size of the object or function in bytes. Here all the fields are 0. Then finally the name of the symbol like .text, .data, main, etc. Next option is -h, which will list high level information. So the command is objdump -h program. So that will include the index number and the name of the section, the size of the section in bytes represented in hexadecimal, the virtual memory address, that is the address where the section will reside in the process's memory once the program is loading and running. Then we have the load memory address, that is the address where the section is stored while the program is on disk or in the initial loading process. Then we have the file offset, the offset from the beginning of the file where the section's data can be found, and the alignment, that request for the section in memory represented as a power of 2. So 2 asterisk 4, meaning the section must start with an address divisible by the fourth power 2, followed by some of the section flags here, some of which are contents showing that the data that should be present in the file. Then there is load, that is the initial data in the file should be loaded into the allocated memory space. Then we have data, which is the data that is writable. Next option is -s, that is used to display the full contents of the non-empty sections within an object or executable file. It will provide a hexadecimal dump alongside the ASCII representation for each section, making it a critical tool for inspecting data embedded in binaries. Command is objdump -s program. So we have the memory offset, hexadecimal dump, followed by the ASCII representation here, which is continued in the second screenshot also. Next we have the command nm, which will list symbols from object files. If no object files are listed as arguments, it assumes the file as a.out. For each symbol, nm shows the symbol value and the symbol type. If there is a lowercase symbol, it means it's local, or if it's uppercase, then it means it's global. So for this also we compile the program gcc add.c -o add. So the object file name is add, so that command is nm space add. So this is the sample output. We have the symbol value in the left column, and here we have the type of symbol and the section it resides. So the lowercase being local and the uppercase being global. Some of the types are T for text code section, D for initialized data section, B for block starting symbol section, R for read-only data section, and U for undefined symbol. Finally, W for a weak symbol. Then there is the symbol name. Next option is -a, that is used to display the symbol table of object files while prefixing each line with the file or archive name. The sample output is shown here for the command nm -a add. Here also, the left side we have the hexadecimal memory address or offset, then the symbol type followed by the symbol name, and before it the object file name is added before the address. Next option is -a, which will display all symbols in an object file, including those typically used only by debuggers. The command is nm -a add. This is the sample output. The fields will be the same. Next option -n, It is used to sort the symbol table output numerically by address rather than alphabetically by symbol name. The command is nm-n add. This being the sample output. Here we have the hexadecimal memory offset. So for some of the undefined symbols, the address is unknown and will be resolved later during the linking process with a dynamic library. There is the symbol type and the symbol name. The file command will determine the file type. So file tests each argument in an attempt to classify it. There are 3 slots of tests performed in this order. The file test, the file system test, magic test and the language test. The first test that succeeds causes the file type to be printed. The file system tests are based on examining the return from a stat system call. The program checks to see if the file is empty or if it's some sort of special file. Magic tests are used to check for files with data in particular fixed format. Language test looks for particular strings that can appear anywhere in the first few blocks of a file. Any file that cannot be identified as being having written in any of the character set listed above is simply said to be data. Command is file space the object file name, which is add here. So this is the sample output. So here we have the details of the executable and linkable format, the architecture details, whether it is little endian or big endian, the computer architecture, the version, etc. is written here. Some of the options in file are the standard usage, which displays the file name and type, is with the option -i. So it will display the MIME type string of the file. So the command is file -i add. This is the sample output. Now we have this as the MIME type, identifying the file as an executable program that is position independent, which is PIE, and the character set being binary, meaning it contains raw non-text binary data rather than a human readable text. In order to display the MIME type string along with the character encoding, using a custom string as separator, we use the option -f. So the command is file -f, the separator followed by the name of the object file. This being the sample output. We get the same output as the previous, it's just that the separator has changed. Next command is OD. Now this will dump files in octal and other formats. It will write an unambiguous representation, octal bytes by default, of file to standard output. With more than one file argument, it will concatenate them in the listed order to form the input. With no file, it will read the standard input. Some of the options being -b, which is used to display the contents of a file as octal values for each byte. Command is OD-b, the name of the text file, random.txt. So these are the octal values. So this is byte by byte in octal format. The first is the offset addresses in octal. For example, 0000040 in octal is 32 in decimal, means the row starts at byte 32 of the file. Remaining is the row bytes of the file in octal. For example, this was the actual content of the file which was written in octal. For example, we'll see the first character is J. So here in the octal representation it's 152. The octal 152 is 106 in decimal, which is J in ASCII value. So J is the 152 in octal. Now option -C will display the file contents as printable ASCII characters, the command being OD-C random.txt. So the corresponding ASCII characters will be displayed. Then the next option is -X, which will display file contents as hexadecimal shorts, which are 2-byte units. This is the sample output. Suppose we take the first entry 6D6A. 6D is hex, whose decimal is 109, whose ASCII is M, and 6A is 106 in decimal, whose ASCII value is J. So 6D6A is MJ. Which is in the sample character these two values. Then the next option is -D, which displays the content in signed decimal format, typically as 2-byte units. The command being OD-D random.txt, this being the sample output. Leftmost column represent the byte offset from the beginning of the file, and this is the data, which is 2-byte unsigned decimal integers. Next option is -A, which will specify the base for printing file offset. AD for decimal, AO for octal, AX for hexa, and AN for no offsets displayed. So we are choosing AN. So the command is OD-AN random.txt. This is the sample output. The first column is the cumulative byte offset from the beginning of the file. Then there is data columns. In order to skip bytes, we use the option -J, which starts from the beginning. So the command is OD-J10-C random.txt. So this was the sample input. And this is the screenshot of the output. So you'll see it skipping 10. So we know it's 2-byte. So skipping 10, we'll skip 1 is 2-byte each. So we are skipping a total of 10, which means 5 of them we need to skip. So J, M, W, I, D will be skipped and F will be printed. Then A, J, S, J and F will be skipped, M will be printed, and so on. In order to limit the bytes, we use the option -N. So the command is OD-N30-C random.txt. So it will print the first 30 bytes of it. Next command is time. So the time command runs the specified program command with the given arguments. So when the command finishes, time writes a message to the standard error giving timing statistics about this program run. So it can consist of the elapsed real time between invocation and termination, the user CPU time, meaning the time spent executing the main process instructions, along with the cumulative user time used by any child process that have finished and have been waiting for by the parent. The third one is the system CPU time, which is the time the kernel spent handling system calls for the process, and the cumulative system time used by all the finished and waited for child processes. Command is time space ls. This is the output. At the end, you can see 3 entries, 3 different time. The first being the real or the wall clock time. That is the actual elapsed time from when the command started to when it finished. It includes the time the process spent waiting for system resources, I/O operations, or other processes to use the CPU. Here it took 0.002 seconds of total time. Then there is user time, which is the amount of CPU time spent executing the commands on user mode code, which is outside of the operating system kernel. So that is 0 seconds, meaning it is a very fast command that primarily involves system interactions rather than complex calculations. The last field is the system CPU time, which is the amount of CPU time spent by the kernel on behalf of the command executing system calls for memory allocation or file I/O. So it spent 0.002 seconds of CPU time in kernel mode. Next command is xxd. So this creates a hex dump of a given file or standard input. It can also convert a hex dump back to its original binary form. It allows the transmission of binary data in ASCII representation but has the advantage of decoding to standard output. Moreover, it can be used to perform binary file patching. So if no in file is given, the standard input is read. If no out file is given, the results are sent to the standard output. The format is XXD followed by options, file, offset and the length. Offset being the start at a specific byte offset and the number of bytes to dump. For a basic hex dump of a file, the format, the command is xxd followed by the name of the file text.txt. So here the leftmost column is the byte offset in the file. For example, 000010 means that is the 17th byte, that is decimal value 16. Then this section will contain the line represented as hex values and finally the ASCII translation of these hex bytes. For hex dump with 8 bytes per line, we use the option -c. So the command is xxd-c 8 followed by the name of the file text.txt. So this sample output will have the offset address. This section with 8 bytes in hexadecimal grouped as 2 byte segments and the rightmost giving the ASCII text equivalent. For plain continuous hex output, we give the option -p. Command is xxd-p, the name of the file text.txt. So this will be the entire byte of hexadecimal characters without any space or offsets. To dump only the first 10 bytes, we use the option -l. The command being xxd-l 10 text.txt. So in this sample output, this is the file offset or address. These are the actual contents of the first 10 bytes of all files represented as hexadecimal values, and this is the text file. To start dump from the given offset, we give the option -s. So the command is xxd-s 5 text.txt. So for this is the offset position in the file where the data begins, followed by the hexadecimal representation of file data, and finally the ASCII equivalent of the hex bytes. Next command is top. Now this program provides a dynamic real-time view of a running system. It can display system summary information as well as a list of processes or threads currently being managed by the Linux kernel. The types of system summary information shown and the type, order and size of information displayed for processes are all user configurable, and that configuration can be made persistent across restarts. This is a sample output of the command top. Here we have the uptime and load average. We have the current time, how long the system has been running, uptime 16 minutes, number of logged in users 1, and the system load average over the last 1, 5 and 15 minutes being 0.99, 0.73 and 0.71. So a load average of near 1.0 indicates a fully utilized single CPU core, while higher numbers show potential overloading. Now talking about the tasks, the total number of processes being 229, the currently running being 3, the number of processes in sleep state 226, number of stopped processes 0 and number of zombie 0. The CPU usage having a very high idle time of 42.7, showing that the CPU is not fully utilized, with a high wait time 23.7% indicating CPU is waiting for IO operation. And the memory with the 7846, that is total physical memory, 512.3 that is available, and 3742.5 total swap space. Followed by the process ID, owner of the process, kernel scheduling priority. There is something called as a nice value which affects the priority. The lower the nice value, the higher the priority for CPU, and vice versa. The range of nice values is typically from -20, which is the highest priority, to 19, that is the lowest priority. Total virtual memory used, then the resident, that is the non-swappable physical memory used, the shared memory size, the process status, then the CPU usage percentage since last update, the percentage of total physically memory used, total CPU time used by the processes, and the command or the program name. In order to show the processes of a specific user, we use the option -u. So the command is stop -u root. This will be the sample output. Here the user will be root. In order to start the top program with a specific refresh delay, we use the option -d. So top -d 20. This is the sample output. In order to run the top program for a fixed number of iterations, we use the option -n. So the command is stop -n 5. This is the sample output. To show the full command path, we use the option -c. So the command is stop -c. Here you can see the entire path is listed here for each command. In order to start the top program sorted by memory usage, we give the option -o mode mem. So the command is stop -o mode mem. So here you can see that the memory is listed in the descending order, highest to lowest. Similarly, for CPU usage, you can use the option -o mode CPU. So the command is stop -o mode CPU. Here the CPU utilization is also listed from the highest to lowest. Then we have the command fuser. So this will identify processes using files or sockets. It displays the PID of processes using the specified files or file systems. In the default display mode, each file name is followed by a letter denoting the type of access. C being the current directory, E being the executable being run, lowercase f for open file, uppercase F for open file for writing, R for the root directory. Fuser returns a non-zero return code if none of the specified files are accessed or in case of a fatal error. If at least one access has been found, fuser returns 0. To find the processes using a directory, we give the command fuser/home/. MEC. So this is the path, and each entry will have a PID followed by the access type letter. So for all of them, the access type letter is C, showing that these processes are using /home/MEC as their current working directory. Now we'll look into a demo on how each of these commands are used. We'll begin with the PS command, which will display the currently running processes for the current user, followed by -a showing all running process across the system. Lowercase a will show the processes for all users except the session leaders. T for those associated with the current terminal. R for the running process. Then we have the process list 1, 2. Then we do it in a command style format using C, U for user oriented format, V for the verbose overview, E for the environment variables, then S for the process statistics including memory usage, then the strace command, which will trace all the write system calls made by the ls command, then the strace command in order to do trace related system calls made by the nc command to connect to a local DNS. Then the statistics of system calls invoked by ls using -c, -r for tracing those with timing information for each call, -o for redirecting the tracing output to output.txt, that is randomtext.txt, the output file. Then we are compiling the program and running the GNU debugger. We give the run command. We enter the sample inputs 1, 2. So that is 1 and 4, which is sum 5. Then the breakpoint. Then the breakpoint with the line number. Then we have the listing of the entire program, listing specific files. Then the next line that is displayed using the command N. Then S for the next step. Then we are printing the values of num1. So we don't see it in the current context. Checking for num2, it happens the same. So we saw that we were stuck with a breakpoint. So after getting over it, we'll get the value for num1 and also for sum minus num2. Then we give the C option for continuing. For backtracing, we give the command pt, finally quitting from the debugger. Then we use the command strings to extract printable strings from the binary executable of ls. Then we give the -a option to extract strings from the whole file, not just sections. Then we use the next option, which is -n for filtering and showing the strings of at least 70 characters. Then the option -f, which is displaying which file each string was extracted from for the specified files. Then the next option for strings is hyphen T, which will display the offset of each string in decimal format. Then there is hyphen E. Here we are treating the file as a sequence of ASCII bytes. Then next we'll compile the program. In order to disassemble it using the next command, objdump, with the option -d. Then the next command being -s to show the source code interleaved with the disassembly for this file. Then -t for the symbol table of compiled program. -h for section headers of executable file. -s for the full contents of all sections of the executable. Then a compilation is performed again. For using in the next command, which is nm. Which will list the symbols from the executable. With the option -a, it will display all symbols including those that are not defined in the executable. Then the file option to identify the file type. -i option for the MIME type. -f option to custom the file field separator for the output when it is being displayed. Then the next command OD. So that will output the contents in octal and ASCII. This is the updated file content. Next option is -c for displaying the contents in character format. -x for hexadecimal format. -d for decimal format. -an for displaying the contents without showing the address offset. -j for skipping specified number of bytes and displaying. Next option -n to output the first specified number of bytes in character format. Time command to measure and display time taken to execute that given command. XXD to create the hex dump of the contents of the text file given. -c option for dumping the text content in hex format with 8 bytes per line. Then -p option for outputting the hex dump in a plain format. -l for outputting it in hex format. -s for starting the hex dump from the byte offset given. Top command to display dynamic real-time view of running process. -u option for filtering and displaying process for the given user. -d option for updating the display every 20 seconds. -n option for limiting the output to 5 iterations before exiting from the top command. -C to display the command line for each process instead of just the command name. Now the option to sort the displayed processes by memory usage percentage, followed by sorting done based on the CPU usage percentage. Then display the process ID of processes using the specified file or directory. That's all for now. Thank you for watching.